Okay, let's get started. Hello, good afternoon or good evening. Welcome to the National Oceanography Centre, Southampton. For those of you who are visiting, just one brief piece of housekeeping. If the bells ring or the alarms go off, it will not be a practice. Just pick up everything, go out of the building and assemble in the car park. Okay, well, it's a great pleasure to welcome you to the National Oceanography Centre, Southampton. I'm Damon Teagle. My day job is Professor of Geochemistry in the School of Ocean Earth Science, based in this building, but I'm also now the new director of the Southampton Marine and Maritime Institute, which is one of the 4 major multidisciplinary institutes in the University of Southampton. So this is probably certainly our first public event of the new SMMI, and it's a great pleasure to welcome a team of coastal oceanographers and climate scientists who have been actively working with the Intergovernmental Panel on Climate Change for assessing this issue of whether we can make 1.5 degrees or what will the impact of reaching 1.5 or 2 degrees of global warming will have on our planet. So there's going to be a series of talks between 4 members of the university academic staff who have contributed to the report that was released today. Then there will be questions and time for a discussion after that. Okay. So first off, I'd like to welcome Ivan Haig, who's a associate professor in coastal oceanography in the School of Ocean Earth Science, who's going to set up the introduction for this session. Okay. Do you want to listen?
Yeah, let's stand them down. Okay, so thank you all very much for coming. So I'm based down here at the Oceanography Centre, and for those of you who haven't been down here before, welcome to the National Oceanography Centre. So I have the very pleasant and relatively simple job of setting the scene, painting the picture. And we're going to start incredibly simple. So first of all, I just wanted to, hopefully all of you know, but for those of you who don't, I just wanted to tell you a little bit about the IPCC. So we're going to start very, very simple. So the IPCC is the Intergovernmental Panel on Climate Change. It was actually set up in 1988, so quite a while ago. It was set up under the United Nations, and they have this fantastic task of trying to provide an objective, scientific view of climate change. Not just that, but also the political and the economic impacts of climate change as well. Now, what's really important, and everyone tends to forget this, but the IPCC does not do science. It is not it doesn't carry out science. It is a review organisation. So it doesn't do any of its own science. It uses existing science from universities, from research organisations, mainly peer-reviewed science, but non-peer-reviewed as well, and sort of synthesizes that. Now, there's 2 different levels of sort of IPCC reporting. And the first is the assessment reports. And we've currently had 5 assessment reports. So in 1990, we had the lovely sounding FAR report, which is the first assessment report. That was followed by SAR, the second assessment report. We then had the third assessment report. And after this, the abbreviation got a little bit more tricky. So we went with AR4, the 4th assessment report. We had AR5 in 2015, and I know Robert in particular and many others from across the university have been involved in that. Currently, the 6th assessment report is underway. The authors were selected earlier in the year, and that is due to be published in about 2021. But there is... and what is really nice is, well, one year, was it 2014, Robert, remind me, but the IPCC shared the joint sort of Nobel Prize with Al. Sorry, 2007. Yeah. Now, with each of these reports, we have 3 main working groups. We have the first working group that sort of looks at the physical science basis. We have the second working group that deals with the impacts, adaptation and vulnerability, and then the third working group that is the mitigation. So there's 3 reports, and then the fourth report is a sort of synthesis, a summary for policymakers. So this is really the sort of key, one of the key goals of the IPCC is to do these reports. They come out about every 6 or 7 years. Now, in addition to this, there's special reports. So outside of this 6 to 7 year assessment cycle, we have the special reports. And there's been probably many tens of special reports over the last 30 years. But there's currently 3 special reports that are being worked on. There's a special report on the ocean and cryosphere, which comes out in 2019. There's also a special report on climate change and land. Again, that comes out in 2019. And then the third is the special report on global warming of 1.5 degrees C. And that actually came out today. And it's nice to go onto the BBC website and see that as a sort of lead article when I switched on my iPhone this morning. And Steve and various others have been on the news over the last couple of days about this. So this report essentially really stemmed from the Paris Agreement. And hopefully all of you know what the Paris Agreement was, but again, I'll just remind you. So the Paris Agreement was set up, again, within the United Nations under the Framework Convention for Climate Change. It's called the Paris Agreement because most of the sort of meeting space took place just outside of Paris. It was actually signed in 2015, but it doesn't start until 2020. 195 members, 195 countries from around the world have now signed this agreement. 181 have become party to it. Unfortunately, we've seen one of the major nations of the world withdraw, and every time I see an American, I try and encourage them to change that view. But essentially, the Paris Agreement committed all of the countries that signed it to this. It said, we will commit to holding the increase in global average temperature to well below 2 degrees above pre-industrial levels, and Phil will come on and talk about that, and really pursue efforts to limit the temperature to 1.5. Again, this is fantastic, but you can see by the sort of level of the, committing to 2 but encouraging to 1.5, it would be nice if we could have encouraged them to get to 1.5, but recognizing that this would significantly reduce the risks and impacts of climate change. Now, what was really interesting is I'm a sea level scientist, and many of the panel that will be speaking today have a sort of coastal or sea level focus. What's really interesting is the Paris Agreement didn't actually explicitly address sea level. However, small island developing states, we sometimes refer to them as SIDS, were one of the key drivers of the Paris Agreement in the places like the Maldives. So they were one of the key drivers of the Paris Agreement. So the Paris Agreement is really why was sort of provided the motivation for the special report. Now, this is the full title of the special report. I'm not going to read it to you. A horrendous report title. It had 5 chapters, 91 lead authors, probably more than 200 contributing authors, 40 different countries from around the world. They reviewed and have cited in the report more than 6,000 journal papers. I read somewhere today that that's, if you stacked all those journal papers on top of each other, it would be about a 20-story building. And they received 42,000 comments. I think, Phil, you were one of the review authors on this. So each of those 42,000 comments had to be addressed and written evidence. So these are the 5 chapters. And really the superstar of today is Dr. Sally Brown, who was one of the lead authors. You're involved in chapter 3, if I'm right. Yeah. So these were the 5 chapters there. So that report was released today. You can go online and you can actually look at that. But a major undertaking, many years of work here. So as I said before, the IPCC does not carry out any of its own research. However, from time to time, it does fund research that can feed into the IPCC report. So really the reason why we're here today is that we have worked on these 3 projects. So the first project here just 1.5. Phil Goodwin was the principal investigation of that, but myself, Robert and Sally were involved in that project. That was funded by NERC, the National Environment, not by NERC. There's also 2 other studies here that Sally and Robert were involved in. Sally did a lot of work for. So these 3 projects weren't funded by the IPCC, but the sort of UK government funded these with the idea that the work of these projects would go into this report. So these 3 projects led to 5 journal papers and a briefing note here, which was authored by the 4 of us here. And what we're going to do is really spend the rest of the time talking about the research that we did in these papers and how those have sort of fed into the broader report. Now, just before I hand over, one of the things I really wanted to stress is the Paris Agreement is absolutely fantastic. I remember watching it on TV when they signed, and just the, really encouraging to see the nations of the world coming together to sort of very seriously tackle climate change. But what's really important to distinguish here is that restricting temperature to 1.5 degrees is fantastic. There is many factors that will come down directly as a result of that mitigation. We will see global temperature come down, and we'll see many negative impacts of climate change decreasing over time. However, sea level is quite distinct, because even Sally will show you this later, even if we reduce temperatures, sea level will continue to rise for many hundreds of years. We call that the commitment to sea level rise. Whatever we do now will not stop sea levels rising. Sea levels are going to rise for hundreds and hundreds of years. And the reason for that is we've only warmed the surface of the ocean. So one of the key components is thermal expansion. As we heat the climate, the ocean expands and rises. We've only heated the surface of the ocean. The ocean's very deep. It's going to take hundreds to thousands of years for that heat to transfer down. The other things as well is we start to melt ice. If you take an ice block out the fridge, it doesn't just melt instantly, it takes time. So there's inertia in the system. So it's really important with sea level rise to recognise that sea level rise won't stop, it will continue for hundreds of years. And so today we want to sort of focus particularly on the sort of coastal and sea level rise aspects of that. So we have 3 speakers now. So Dr. Phil Goodwin is a lecturer here in Ocean and Earth Science with me. He's going to take over next and talk about the sort of projections. Dr. Sally Brown is a research fellow in engineering and the environment. She's going to come in and particularly talk about the sort of sea level rise and the coastal, mainly the coastal impacts. Robert will take over. Robert's a professor, again, in engineering and environment, and he's going to talk about the implications. I'll then bring it together at the end and just have a look at the summary, the main synthesis from the report, and then we will open it up to questions. So I'll pass over to Phil now, who's going to talk about projections.
Thanks, Ivan. So to start with, let's think about can we reach 1.5 degrees C, and let's put that into a historical context. That's not the right one. So, if we look here, we can I've plotted a graph of the global mean temperature reconstructions over time. And politically, there's been this agreement to restrict warming to 1.5 degrees C above pre-industrial. Now, the industrial era began around about the late 1700s, but we only actually have accurate temperature reconstructions going back to 1850. So there's a bit of ambiguity as to what is the temperature anomaly relative to pre-industrial. Generally, people looking at the graph here conclude that there wasn't much warming before 1900, and so we use the average from 1850 to 1900 as our pre-industrial baseline. But there is a little bit of uncertainty there about what actually pre-industrial means. Now, the special report today concluded that from observations so far we've had about 1 degree centigrade warming, with a likely range of about 0.8 to 1.2 degrees. If we just look at the recent rise in temperature from the 1970s to the present day, temperatures have been increasing roughly linearly with time, And if we just plot that out into the future, you can see that we're on course to exceed 1.5 degrees C at some point between the 2030 and 2052. This means that to stabilise climate at 1.5 degrees C, we are clearly going to need to reduce our emissions of greenhouse gases. This includes primarily atmospheric CO2, but also other greenhouse gases such as methane and nitrous oxides. And we'll also go through the 2 degrees C barrier this century if warming continues at the current rate. So this is observations up to now. We can also think about what happens to climate model simulations going into the future for different mitigation scenarios. From the last assessment report 5, this figure shows different climate projections for a range of the state-of-the-art climate models out into the future for some different mitigation scenarios. The red line shows us what happens if there's no attempt to reduce emissions. So we just allow emissions to keep increasing as the economy grows and the population grows this century. In that case, we'd see something like about 4 degrees warming by the end of this century, extending to around about 8 degrees warming by the year 2300. So a very drastically different world in the future to the world we're accustomed to now. The light blue scenario shows what happens if we have some mitigation in the first half of this century, out to 2050, but then after 2050, we introduce strong mitigation. So we do everything we can after 2050 to reduce our emissions. And as you can see from there, we end up with something like 2 degrees C warming at the end of this century, going a bit above 2 degrees C in the centuries that follow. If we want to get to anything close to 1.5, the only scenario where the complex climate models show we get down to close to 1.5 is if we have strong mitigation measures starting now. So we need to do everything we can. The dark blue scenario is where we do everything we can to reduce emissions of greenhouse gases starting now. And that way we get something like about 1.5 degrees C warming by the end of this century, and then coming down slightly going on into the centuries into the future. So the only way we can get to 1.5 is if we have strong mitigation starting now. Delaying things won't be good enough. We can also think about the level of mitigation required for 1.5 degrees C. Precisely how much mitigation do we need to do? What do we need to do to carbon emissions? Here I'm showing you a plot of surface warming, the temperature anomaly, against the total amount of carbon emitted. And I've zeroed the graph at the carbon that we've already emitted at 2017. So the negative numbers are carbon we've already emitted, and then the positive numbers are carbon we are going to emit in the future. And we can see when we plot a graph out like this that warming increases roughly linearly with the total amount of carbon emitted into the system. So the more carbon we emit into the system, the warmer temperatures are going to get. And I put a quote here from today's special report. Limiting global warming requires limiting the total cumulative global anthropogenic emissions of CO2 since the pre-industrial era. An important implication of this is that if we want to stabilise climate at 1.5 degrees C, at some point we need to be a carbon neutral society. So we need to get to a point in time where we no longer emit any more CO2 going forwards. If we do, we will, however slowly, keep moving to the right of this graph, and the temperatures will keep increasing and increasing. So the important question is, how quickly must we achieve a carbon neutral society if we're to keep warming at just 1.5 degrees C? And what the special report today concluded was that we need to get a net zero emissions society by 2050. with an uncertainty of around about plus or minus 5 years. So we need to be absolutely carbon neutral by 2050 if we're to be on course for 1.5 degrees. That's shown here as the grey scenario. On the left-hand side, I'm showing you the warming over time. The grey scenario levels off at 1.5 degrees C, and you can see on the right-hand panel, that's the annual emission rate over time. We need a very drastic decrease in our emission rate. We have a little more time to become carbon neutral if we want to limit warming to 2 degrees C. For 2 degrees C, we need to reach net zero emissions by around about 2075. And that's shown by the blue scenario here, where warming levels off at 2 degrees C and we decrease carbon emissions to zero, taking a few more decades to achieve that. And we can compare that to the purple scenario, which is where we just let emissions go out of control, increasing and have no mitigation measures at all. And in that case, the emission rate will roughly treble by the end of this century. So these are two very different societies we're thinking of. One where we have zero emissions, and another one where we're emitting 3 times as much carbon as we are today. Also, we need to deal with the other greenhouse gases. So this figure, the big plot on the left-hand side, shows what we need to do to atmospheric CO2. If we focus on the light blue lines, we see emission rates need to fall drastically and get to zero by around about 2050. After 2050, it's likely that we'll need some net negative emissions. We'll need, globally as a society, to capture carbon, a small amount to hold warming at 1.5 degrees. On the right-hand side are 3 panels showing what's happening to other greenhouse gases or aerosols. The methane emissions and the nitrous oxide emissions, they don't need to come down to zero. We can still emit a small amount annually of those greenhouse gases. And the reason for that is those greenhouse gases stay in the atmosphere for a lot shorter time, and so we can keep emitting a small amount, and the levels in the atmosphere won't increase too much. So the key messages from today's special report on 1.5. We've had already 1 degree of warming so far, and we're on course to exceed 1.5 between about 2030 and 2052. No mitigation sees about 4 degrees of warming, and we need strong mitigation starting now to have any chance of getting to 1.5. For 1.5, we need to be carbon neutral by 2050, and to show you what that means on the way there, something a little closer to that time, we would need to reduce global emissions by 45% by 2030. So a very drastic change in our society to make that happen. Okay, so that's all I'll say on climate projections, and I'll pass you over to Sally to talk about impacts.
Hello everybody. I'm going to be talking about what the impacts of sea level rise are. I'm going to be talking about global scale sea level rise rather than going into detail, which Robert will be covering in the next presentation. Oops, that's the wrong way. Right. So the first thing is asking the question, what does a 1.5 degree world mean for sea level rise? And this is something which we asked at the very, very beginning of our research. So here I'm going to show you several scenarios, and we've got a series of scenarios. Let's just check that works. Yep, there we go. These are our scenario names. They're called adjusting mitigation pathways, AMPs, but the one thing that you need to focus on is not the letters, it's the numbers at the end, because that gives you an indication of the temperature rise. So our 1.5 degree scenario is known as AMP 1.5, and that's the grey one. At the AMP 2.0 is at 2 degrees, and so on until we get to the red one there, AMP 4.5, which is at 4.5 degrees. We also looked at a non-mitigation scenario, a representative concentration pathway scenario 8.5, which has a lot higher emissions again. And so it's this family of scenarios that we analysed. And in sort of the next few slides, I'm going to be concentrating on the purple one, the non-mitigation scenario, RCP 8.5, and the 1.5 degree scenario, which is the grey one, which will come up at the bottom. So in this figure, along the y-axis, you've got sea level rise, so going from naught to just, we call the present 1986 to 2005, right up to 6 metres. And along the x-axis, we've got from just before 2000 in time, going all the way along to 2300, so a very long time frame here. The black squiggly line shows how much sea level rise there's been so far. Now, I'm going to add in, this is the 1.5 degrees scenario, and you can still see it's starting to increase. This is the 2 degree scenario, the 3, the 4, sorry, not going to say if that's the 3, the 4.5, and this one is RCP 8.5, the one if we don't mitigate climate change. The first thing you can see from here is that the one where we don't mitigate is very, very different from the ones where some degree of mitigation occurs. So the purple one is very much higher in terms of the level of sea level rise and the amount of temperature than these lower ones where we mitigate for mitigate for climate change. By 2050, the sea level rise that we expect in any of those scenarios is between about 24 centimetres if we take the 50th percentile of uncertainties. By the time we get up to 2100, the 1.5 scenario, the grey one at the bottom, is about 40 centimetres. But the purple one, the non-mitigation scenario, is 78 centimetres by 2100. So even when we take account of the next 80 odd years, we're really seeing some benefits of climate change mitigation. But the real story isn't about what happens at 2100. The IPCC likes to cut off at 2100 because it's a nice cut-off point in graphs. But we know sea levels will keep rising after that, and this is where the real sting in the tail comes, is that sea levels will keep on rising because, as Ivan said initially in the first part of the talk, it takes time for the oceans to absorb the carbon dioxide, and it has an increase in temperature and an increase in ice melt as well from glaciers and ice sheets. So by the time we get to 2300, we're looking at multi-metre sea level rise as opposed to about 1 metre when we look, if I just put that one there, that's it, to look at the contrast of 1.5 degrees. So that is really a very important message, that climate change mitigation, it won't stop sea level rise. Even if we stopped emissions, it won't. It would just stabilise the rate of increase of sea level rise. So we found our results, but what does this mean compared with the IPCC report? This is a table in Chapter 3 of the report, which details how much sea level rise could be expected across a range of studies at 1.5 and 2. Now, I've put the light blue boxes there, are the ones that I just want to talk about at the moment, and our study, I don't know whether you can see it with the chairs in the way, it's right at the bottom. In essence, what we found is that our studies had a similar lower end of uncertainty, but were a little bit lower at the high end. IPCC summary for policymakers said that they expect a 1.5 to 2 degrees scenario to be somewhere between 26 and 77 centimetres of sea level rise by 2100. And they also expect that there may be maybe just 10 centimetres difference between a 1.5 and a 2 degree scenario. So the uncertainty is a lot more than actually what the individual scenarios are. So there's still a lot of learning and understanding, and also a lot of control in terms of what we could do in terms of emissions to actually influence that end point in 2100 and then beyond. So what does that mean in terms of impacts? The sea level rise is so what? Well, when we look about climate change, it's not just about sea level, it's also thinking about storms and waves and increases in temperature. It is also thinking about carbon dioxide concentrations and runoff. And that actually affects the coast in many ways. The coast isn't just about the sea, it's also about the land. So we also have to think about what the terrestrial influences are, as well as the marine influences, and understand how that coast is affected as a mix between a natural system and a human system. And Robert will go into this a little bit more in deltas in his section. And when we think about those impacts jointly, and particularly sea level rise, we get effects such as perhaps increased erosion, flooding, particular salinisation, that can have far-reaching effects within the environment and society. In this slide, I just want to think about what it actually means globally. So what will flooding, how much land, and then secondly, people will be potentially flooded or be exposed to extreme events if we continue with sea level rise. It's a bit of a complicated figure, but the thing I want to concentrate on is this top box here, which is the 1.5 degrees scenario. It's where we have a lot of climate change mitigation. And oops, where has it gone? The bottom one here, which is the non-mitigation scenario. That was that really big purple one. Along the y-axis, we've got the amount of land which is exposed to flooding. So, and then along the x-axis, we've got time. The first thing to say is actually there's a lot of land which is potentially exposed to flooding, so extreme events, maybe a 1 in 100-year event in this example today. It's about 540,000 square kilometres, which is roughly the same size as New Zealand. But by the time we get to 2100, when we're thinking about a climate change mitigation scenario, so this top one here, if we're looking at the 50th percentile, that increases to about 610,000 kilometres. But that's nothing compared to when we're thinking about the non-mitigation scenario, whereas it goes up to about 740,000 square kilometres of land that could be potentially flooded. We then need to think about the people who live on the land. And that gets a little bit more complicated again, because we don't just have uncertainty in what's going on physically with sea level, we also have population growth as well, or population decline in some areas. And so that can really skew the figures. We might actually have less people exposed to flooding in the future, just because there's less people on Earth. So we looked at lots of different socioeconomic scenarios, lots of different scenarios of population change, which are numbered along the top here. They're called shared socioeconomic pathways, which are SSPs. I don't want to again focus on the detail, but I just want to say there are lots of different possible outcomes in the future about how many people could be exposed to flooding. It's not going to be a one set answer. But the indication is we're looking again from around about 100 million people exposed to flooding today, about 65 million people in the UK, to give you some comparison there. By the time we look to 2100, there could be potentially a lot more people again, particularly if we see lots of population growth in low-lying areas such as deltas. But it doesn't stop there. When we go on to 2300, all of these numbers just keep on increasing. There's going to be more land that's going to be exposed to flooding. There's going to be more people that are exposed to flooding. And potentially somewhere between 1.5 and 5.4% of the world's population could be exposed to coastal flooding by 2300. So we are talking about millions of people. This is going to be a big thing, and it's not going to happen now. It's not going to happen in the next 50 years. We're going to be looking at 100, 200 years' time, where these effects are really going to kick in because of our actions today. It's not just people on the land, it's going to be happening underwater as well. This is a study, this is led by Robert Nichols. It was in the Field Trans paper, which was a group, one paper within a group in a special issue that particularly looked at the 1.5 degree question. This time we've got a slightly different set of scenarios, little colours of scenarios. We've got RCP 8.5, the non-mitigation scenario in red, and we've got our 2 degrees in blue, and then the 1.5 degrees there in grey. Again, same message as before, temperatures will keep on rising. But this time we also looked at pH as well. And this is where it gets really quite, you see very different things. We do start to see thresholds, and suddenly this pH starts to decline. And that becomes very worrying. The IPCC report specifically states that we've seen evidence for oceanic temperature rise. We've also seen evidence of ocean acidification, and that's going to affect corals. And one of the main things that comes out of the report, and it's been on the news headlines today, that corals will be seriously affected by climate change. And there is that fine line between what happens in a 1.5 degree situation, say compared with a 2 degree situation, on the future of corals. The summary for policymakers states that corals may decline by a further 70 to 90% at 1.5 degrees, but it could be up to 90% with 2 degrees. And that's really quite shocking, that we might not have any more corals when you're talking maybe by the time I get very old, hopefully within my lifetime. Sorry, not hopefully the corals will die, but hopefully I'd live a long time. So climate change mitigation has many benefits. It's not just about, say, with corals, thinking what happens, it's also the environments they support in terms of the fish, the fisheries, the ecosystems, the natural protection and also tourism, which is very important if, say, you've got a close connection with the coast, you're a small island, you rely on tourism. So it can affect development sustainability too. The message here is that when we're talking about ocean systems, it's not just talking about the long time frame, which in my research area we talk about a lot. So sea level rise, the impacts are going to be more in the far future, but what we're doing now will affect it. For corals, it's going to be happening. It's happening now. We see it on short-term increased temperature events in the ocean, such as El Nino. It's going to be happening in the next few decades, and that is something to be really worrying about. And these timescales are really very, very important. So my key messages here is that climate change mitigation helps stabilise the rate of sea level rise. Sea level rise isn't going to go away. It's going to vary a little bit, but it's going to be here to stay. Sea level rise, with our studies, it's going to rise approximately by 40 centimetres by 2100, but potentially double that if we don't mitigate. And that rise is going to continue. The land exposed to flooding is also going to increase. And if we keep building on the coast, if we build cities on the coast, those many more people potentially be at risk. And again, Robert will cover that in his presentation. The number of people that are affected, potentially, if we have population growth as well, will also increase between about 1.5 and 5.4% by 2300. And finally, ocean acidification will have severe effects on corals and their organisms and ecosystems and population who rely on them. And so we've really got to think about actions that we can do now. We need to think about the impacts now, but also the impacts that could happen potentially in the far future as well. And with that, I'm going to hand over to Robert, who is going to be talking much more about the more local and regional implications of sea level rise and some of those hotspots around the world. Thank you.
Okay, so thank you. And so I want to take this view of implications, focusing mainly on sort of sea level rise. I'm going to look at small islands, I'm going to look at coastal cities, I'm going to look at deltas, and then I want to sort of join it together in maybe some of the issues around what we do with this fact that there's a commitment to sea level rise. So I'll start with small islands. Now there are many small islands, or SIDS as was said at the beginning, are one of the main reasons for the Paris Agreement. And these are the Maldives in the Indian Ocean, both a map and a picture. They're atolls, so they're some of the lowest islands. They're sort of really only within 1 or 2 meters of current sea levels, formed by wave action taking material from the coral reef. And these are kinds of pictures that you just see if you go there. And it's self-evident that if we have 80 centimetres of sea level rise by 2100, the unmitigated rise in sea level, that a place like the Maldives has really big problems. You don't need to run any models to see that there's going to be great changes and great challenges. And if we think to 2300, roughly 4 metres of sea level rise, well, complete submergence of these systems is certainly something that gets discussed in a sort of plausible way. But let's remember then, if we achieve 1.5 degrees, by 2300, we're still, well, by 2100, we're still seeing 40 centimetres of rise, and 2300, it's a long time into the future, but sea levels are above the value of unmitigated sea level rise in 2100. So basically, mitigation here is giving the Maldives an opportunity to adapt to these problems, but it's not letting them off the hook in terms of impacts. The point about coral reefs that Sally made is also very important, that with 1.5 degrees, we've probably got healthy ecosystems there that might sustain it. The scenario of unmitigated means maybe all the ecosystems are dead, and that will be a further adverse impact. And we have to think when we're adapting in the Maldives, not just about these beautiful islands where the tourists go. This is the capital. It's 100,000 people in Male living on 2 square kilometres of land. In the background, you can see an island, Hulamali, which is the airport, and they're actually building a new island to take the same number of people because of the pressure of population growth. So we've also got to think about these very urban settings within islands, and how do we adapt these if we think about even with the 1.5 degree over the long term. Thinking about cities in general, Male is a city with less than 1 million people, so it doesn't actually appear on this, but these are the cities with more than 1 million people in 2005 on the coast. There's 136 of them, and they are sort of hotspots of where we will see impacts with sea level rise, and also they're hotspots where we'll need to adapt if we're going to deal with these problems. So they're where we see the maximum benefits from mitigation to 1.5, but we have the commitment. And if we just think about one of the cities, one we probably, most of us will know quite well, London, the Thames Barrier. This is the 100th closure of the Thames Barrier, so it's meant to flood like that. This is downstream. It's protecting the area beyond the barrier. You can see Canary Wharf in the distance, so it's doing its job. And again, you don't really need to do much in the way of analysis to see that if we see 80 centimetres of sea level rise, that isn't going to overtop the barrier. But when we start to think more extreme events, the likelihood is going up. And as we move into the terrain in unmitigated rises of 4 metres, well, it's going to completely submerge this place. But even then, if we think about 1.5 and the rise of maybe something like a metre by 2300, this structure is still going to need to be adapted. So really, in all these coastal cities, again, just like in the Maldives, we're going to need to be thinking, well, the 1.5 degree report makes out the point that we're going to have to be thinking about some adaptation. So mitigation is making the problem manageable, but we're still going to need to adapt. And this point isn't probably made so strongly in the report, but I think it is an important point to acknowledge. Deltas are another very vulnerable area around the world's coast. There's 500 million people living in deltas. This is where basically river sediments are carried to the sea, and we have huge areas of land, 1% of the area of the land, with 7% of the people living on it, all fairly close to contemporary sea levels. The circles are showing you the size of a number of deltas. It's not a universal sample, and the colours are showing you density. So the very dark blue ones are showing you where lots of people live. So you can see in Asia there are lots of deltas, and they tend to have a lot of people living in them. And we took with it, I'd like to look at 3 deltas we looked at in particular within a project called DECMA, which a number of people in the room have been working upon, which is funded by the IDRC Canada and DFID. We looked at the Ganges Brahmaputra in Bangladesh, the Mahanadi in India, and the Volta in Ghana in West Africa. And these areas, as with the floodplain that Sally was talking about globally, they have quite significant areas that are below flood elevations today. Often there are defences there to stop these areas flooding. But if we look at the red line, which shows what happens with the unmitigated scenarios, and again we're going from 2100, from 2000 to 2300, so we're taking a long timescale view to look at this big picture of what happens. We see that really the deltas, the floodplain area doubles, or in some cases almost even goes up to 3 times the area that it was today or recently, but with the unmitigated, with the mitigated scenario, we see a slower rise, but it's still an increase in the floodplain. There are additional factors that aren't considered in this diagram. Deltas do tend to subside, so they're actually losing elevation, not due to climate change, but due to the compaction of sediments. So that would make this worse. Equally, there's sedimentation going on in deltas, and that can balance this process, although we tend to exclude sedimentation with flood defences. So there are other processes going on which need to be thought through. So I've made the point that with the 1.5 mitigation, we bring sea level rise right down, but we've only stabilised the rate of sea level rise, and we need to adapt. So what kinds of things could we actually do in the face of this challenge? And this is a very sort of classical picture that's been around for 30 years or so, since the first IPCC report, showing we can retreat, we can move landward, we can accommodate, we can change how we use the land so that it's so although flooding, say, happens or impacts happen, it doesn't bother us. We put our houses on stilts, or we can protect. We can build barriers which keep the sea out, be they hard or be they soft. And this is kind of the classical view, but there are some other things to think about. And I think one of them, which is attack or advance, we actually see, and we're standing here in the National Oceanography Centre, which is on land that was formerly mudflat, so we're in an area where we've advanced seaward in the late Victorian period to enhance the docks of Southampton. But in the last 30 years, 30,000 square kilometres of land has been taken from the sea by coastal advance. And so we can think about, well, maybe we should be, if we're going to be doing this, we ought to be thinking about the fact sea level is going to rise, and we ought to maybe be allowing for that and building higher in terms of elevation. And in fact, in the Maldives, I mentioned they're building new islands, and they are actually factoring in an allowance for sea level rise. So they've already taken on board that idea in the Maldives, but that's by no means universal. It's often ignored. There are no real standards, if you like, for how to deal with this. So that's something that needs to be developed in the future. And also, there's increasing interest in nature-based adaptation and working with nature. And there's a lot of people trying to understand. We understand engineering defences very well. How can we understand nature in the same terms so we can actually see what benefits we might get from that? And I mentioned that, the Maldives, one of the benefits of 1.5 degrees stabilisation would be that we actually keep those nature-based services so that we have them, and if we have very large climate change, we may lose them or they'll change. Equally, this idea of sedimentation in deltas, and actually maybe some kind of engineered or controlled flooding where sediment is available to build elevation, is another way forward. I think when you think about, London has the Thames estuary has a big plan about what it's going to do about flooding, which is quite unusual. There aren't many of these plans, and we need to see more of them. But in that, you would see a portfolio of adaptation measures. It's not about doing one thing. It's about doing a number of things that work together effectively over time. And equally, it's not something we have to do today. It's something that we have to do today. To some degree, our children will have to do more, our grandchildren will have to do more, and so on, because the rise keeps on growing. So we can think about this as pathways or sequences of measures with time or with the magnitude of sea level rise. And I think this work suggests that we ought to be thinking about thinking in these terms for coastal areas and how they might develop over the coming decades and centuries. What about the barriers or limits to adaptation? It's easy to talk about adaptation. Well, what might actually stop us adapting or cause problems? And we've looked at that in a recent paper in Nature Climate Change. And we recognised there are sort of maybe 4 different types of limit. There's technological limits, something, at some point things fall over. Economic barriers, maybe it costs more than it's worth. Financing barriers, getting money to actually deliver projects. And society, social conflict, the fact there are winners and losers. So if you try and do something, you can't make a decision because so there's not a political consensus that this is a good way forward. And what we find really is certainly in cities, so whether we're talking about lots of people, technology and economic barriers are quite minor, really. There's a lot of technology available, and certainly it makes sense to protect all the coastal cities I showed you from a cost-benefit point of view. There are barriers in financing. Just because something is beneficial in the cost-benefit sense doesn't mean you can actually get people to pay for it. And socially, there's an awful lot of conflict, and you see that in all the sort of places that we looked at. Interestingly enough, those 2 barriers, the financing and social conflict barriers, are not really looked at very much at all. So some key messages. Overall, from sort of trying to draw this together, and I think the first point is that climate stabilisation, 1.5 degrees is an example of climate stabilisation, but in general, climate stabilisation has rapid benefits on the temperature-related climate change factors. So, ocean pH, for example, we can stabilise that if we get stabilised climate very quickly, and even factors like storminess. We haven't really talked about that, but that would be linked to temperature. But we've said this several times, but I think it's worth emphasising, which is why we put it in several times. It will stabilise but not stop climate-induced sea level rise. There is this commitment which continues for centuries, and in many ways, you can see this as a commitment to have to adapt to sea level rise. So you have to do something about it. And interestingly, if you actually wanted to stabilize sea level, you would have to have global cooling. Okay, we'd actually have to make the planet colder if we wanted to stabilize sea level. If that was our sort of policy objective. Given that we're stabilizing sea level, I think the most appropriate climate policy response for coasts, particularly for sea level, is a combination of climate mitigation to make sea level rise manageable and adaptation to this residual sea level rise. And such adaptation is going to need to be an ongoing process, and we've got to consider these issues of barriers, constraints, but equally innovations and opportunities. We're definitely via modelling, etc., developing new ways of thinking about adapting, warning systems, etc. So there are going to be new ways probably that we can deal with these problems that have been developed or maybe haven't even been thought of yet. So with that, I'll pass back to Ivan.
Thank you. It's really interesting. I was with the Environment Agency last week discussing the Thames Barrier, and it's just a really nice example where they have a plan in place and they are confident they can protect London to 4 or 5 metres of sea level rise if necessary. Unfortunately, that doesn't apply to other parts of the world. So what I wanted to do was one final last thing. I gave a talk to students this morning about giving a good presentation, and this is the sort of slide that I encourage them all to avoid. It's hideous. But we wanted to show you, these are the actual wordings that are used in the sort of summary for policymakers in the report. So let's just go through some things very, very quickly. So first of all, the report stresses that from 1.5 degrees compared to 2 degrees, it's only about 10 centimetres of sea level rise lower, and hopefully on the discussion we can come back and discuss that. We've already stressed several times that sea level rise will continue well beyond 2100. We have very high confidence in that. The amount of sea level rise we see is obviously very dependent on the future emissions. And as we stressed earlier, with the RCP 8.5, we could see 4 to 5 metres of sea level rise compared to 1 metre with 1.5 by 2300. So it really shows you we have to think about those long time scales, and mitigation is really, really important now. The slower the rate of sea level rise, particularly if we can achieve 1.5, means there is more time for adaptation, as Robert says, which is very important for sort of ecological systems, very important for these 3 regions: small islands, low-lying coastal areas, and deltas. In terms of the values, we've seen that with 1.5 we expect somewhere between 26 and 77 metres by 2100. Our projections, Phil, were coming out at about 40 centimetres, I think. It's about 10 centimetres higher for 2 degrees. Not much of a difference by 2100, but by 2300 that difference is a lot larger. Having said 10 centimetres is quite small, a 10 centimetre reduction in sea level equates to 10 million fewer people being exposed. That's based on the population today. We've already said that sea level rise will continue well beyond 2100. We've got very, very high confidence in that. Phil's projections, our projections show that we can expect at least a metre by 2300. Now, what we haven't sort of focused on is there could be instabilities in the system. I was speaking to Jonathan Bamber at Bristol University, and certainly when we get above 1.5, somewhere between 1.5 and 2 degrees, we could start to see major instabilities in ice sheets, particularly in Greenland and the Antarctica. If these do occur, then we could see many multiple metre rises in sea level, well beyond sort of 4 metres. There's still some uncertainty in that, and that's definitely an area for future research. So just finally, we've looked at the exposure to small islands, low-lying coastal areas, densely populated deltas. It's not just about sea level rise, increased flooding and damage, but there's saltwater intrusion. There's many islands, certainly in the Solomon Island chain, where we're starting to see communities having to move off islands because of saltwater intrusion affecting crops. And Steve Darby, you were on the BBC the other day talking about this from the Mekong Delta perspective. I think I will finish there. So what we're going to do now is I can just invite the speakers back on stage. I'll turn over to Damon, who's going to open the floor up to questions. Could we make sure that when you put up your hand, when Damon points to you, could you just wait for Abby to pass you a microphone? We're videoing this event and we just want to make sure that whoever watches it afterwards can hear the question. So Abby, can I just pass the microphone? So please, before you ask a question, just wait for Abby to come to you.
Okay, first off, just while Ivan's sitting down, I think we should thank our speakers. Okay, questions from the audience. At the back there. Just wait for the microphone, please.
In your summary, the start of your summary, you made reference to the Thames Barrier. But I point out the Thames Barrier wasn't built for sea level rise, it was built for surges. And when we were looking at what level should work to, we took into account mean sea level rise, we took into account the dredging, which meant that potential energy was going to push it up higher, kinetic energy was going to push it up higher. We also looked at what was called the Rossiter effect at the Dr. Rossiter at the Liverpool Tidal Institute, which took into account events. And for places where you've can build a barrier, it is important to look at the events. The simple end is the mean sea level rise. It's what the climate change is going to have on frequency events and how big and frequently they're going to occur.
I'll start, Robert, and you can jump in. So in the paper that we wrote with Phil, we looked specifically at extreme sea level events as well. Now, if we focus on the last 100 years, we see that mean sea level has risen by about 20 centimetres. And what we find is there's very good evidence that we've looked at many long time gauges sites around the world. We find that the extreme sea levels are increasing as well. And what's basically happened is the frequency at which high sea levels are exceeding has increased enormously. Now we find that in 95% of the time gauges around the world, what's predominantly driving that is mean sea level. We find very little evidence that storm surges are getting stronger. Now that obviously might change in the future, but certainly over the last 100 years, most of that changed. And certainly the work that we did with Phil, we find that levels that are currently only being exceeded once every 100 years, even with small changes in sea level, are now being exceeded every year. And into the future, we find that, again, a 1 in 100 year event today would occur almost every single tidal cycle, just under very normal conditions. Now, what's really interesting is last week I gave a presentation to the ice storm workshop, which is storm surge barriers all around the world, but we spoke quite a bit about the Thames. It's really interesting looking at the Thames Barrier because I'm really trying to establish, Robert and I have met with them 4 or 5 times over this year, we've got a NERF funded project. What is the real limit with the barrier? They were very, very conservative in building it. They took account for changes in tidal range. But they say the real limit is when the Thames Barrier closes 50 times a year. Once we start seeing 50 closures a year, it becomes uneconomical to run it. And it's not just the cost, it's not actually the cost of each closure, it's that when you get 50 times a year, there isn't enough time in between closures to carry out the necessary.
Yeah, that is the biggest problem, is that once you get that surge effect and you put the barrier in place, you're going to be there for 3 or 4 times possibly in the future. So it will increase it by a large number of help. And what hasn't been taken into account, which I didn't refer to, was the effects of surface runoff, which you've got to close the barrier so as to allow enough volume behind the barrier to take into account the amount of water that's coming down. And that is also due to events. we're getting more and more heavy events of rain. So the simple bit is filling the sea level.
Well, I was just going to say, I think, basically, I agree with everything you said, but I think that the key point is that mean sea level does drive up the extreme events, as I just said. And that's been, the Thames Barrier actually did include a ½ a metre allowance for rising high waters in its design.
You also included reflective wave, which now, when you operate basic barrier more frequently, you know how to use the barrier properly.
But anyway, we shouldn't get too much involved in infrastructure, but there are interesting things to do with overturning. You can get a little bit more out of it, but ultimately, as Ivan said, once it gets to a certain frequency of closing, you have to build a new barrier downstream or abandon London. I mean, that's your choice.
Just geographically, let's move into the front of it. Yeah. Just quickly get the Selma, then you, and then back to
Dr. Goodwin, you mentioned that after 2050 we're probably going to need an negative carbon budget. Is there any way of quantifying this? Like how much carbon will we need to kind of take back from the atmosphere after this time in order for it to be
the kind of range in simulations tend to be from sort of just negative to up to around about a tenth as much taken out as we're currently emitting, something like that. So we're currently emitting about 11 grams, and we might need to take out up to 1 gram a year. In terms of how you actually accomplish that, I think that's an open question. I'm not sure. We're running these current models, assuming that it's feasible, but I'm dubious as to whether that actually is.
But the amount of CO2 that you'd have to capture and then store some way would be a volume equivalent to total liquid fuel hydrocarbon production on the planet today, possibly more. So that would require a whole new industry to be able to move those sorts of volumes around, which doesn't exist at the moment. Someone. Yeah.
So firstly, are we doing enough? Currently, no, with the policies that are currently out there, that's not going to achieve anything like the carbon society projects or by any time. There's a lot of activities we currently do that we have no way of powering them sustainably. There's no way of flying sustainably. There's not really at the moment, I don't think, a way of transporting goods across the sea sustainably. So yeah, at the moment, no. Some of the other things, that is globally. It has to be everywhere, it has to be carbon neutral. I certainly don't think there are any large countries that have any plans to realistically become carbon neutral. There might be some small states that have the ability to become carbon neutral, but not for any large countries.
There was a question at the back, and then you, and then you. Okay.
I think another issue, I found this fascinating. Before I retired, I worked in this area for quite a long time. But another issue, both locally for this country and other parts of the world, is how sea level rise impacts the drainage of low-lying areas. In this country, a lot of low-lying areas which drain during the intertidal period because they can, it's the relative levels. But as we move with higher sea levels, will struggle, and there'll be need for pumping probably. And I think again this is how we in this country and elsewhere should think about where we should develop areas and not develop inappropriate areas.
Well, I think you're absolutely right. I mean that as sea levels rise, we're going to have a lower and lower periods that we can discharge under gravity, and so either you accept greater risk of flooding, or you have to move to other means to discharge the water. Even with land use, I mean, you can see somewhere like Canvey Island. I mean, if the land use changes, you often go to pumping simply because if you go from a rural to an urban setting, then people will accept a much lower frequency of flooding, and this is going to happen globally. So these are global, these are coastwide phenomena. If we stay put, the obvious alternative is to think about some kind of retreat. But if you're going to stay put and you're going to protect, part of protection is not just the wall; it's keeping the land behind, the low-lying land behind dry. And that, I agree with you absolutely. You have to think about that as part of the problem.
There was a gentleman here, and then a woman here, and then a gentleman here.
Okay. How sustainable are flood barriers? And maybe I missed this in the talk, but what are some examples of natural-based flood mitigation or flood protection measures?
Well, I think if we take the second question first, I'll go back to the flood. I mean, I think that we increasingly recognise the value of the protection that nature gives us in terms of if you have a salt marsh and during an extreme sea level event, it will take down, it will dissipate a lot of the wave ending, for example, so that the defences behind it can be smaller, or buildings behind it may not get flooded at all. Or a sand dune. I mean, the sand dune provides a natural barrier for defence. And for certain types of defences, the Netherlands, the open coast of the Netherlands, is essentially a set of managed sand dunes. They're some of the biggest sand dunes you see in the world, really, and they're continuous because they've got water coming into the lower end behind. So with sort of beaches and dunes, there's a lot of experience in using those approaches to protect. We also see that things like salt marshes are often in decline, so these natural defences are going, and that we end up substituting them with artificial defences to build higher walls or whatever. So there's a lot of move to try and understand marshes, coral reefs, seagrass, etc., in the same way that we would understand an engineered system, so that we can actually start to compare them and actually make decisions. And I think in reality, some people talk as if we can replace engineered systems with natural systems. I suspect it's more hybrid, about trying to get things that work together. So that's really, I think that's a big research and development exercise. There's a huge amount of interest in it. If you go to meetings on adaptation, you hear a lot of people talking about projects of this type, like their great successes. I'm very sceptical if there are many successes, because it's brand new and we haven't really had a chance to assess it. But we're trying to learn, and I suppose learning by doing is one useful way to learn. In terms of are storm surge barriers sustainable, I suppose the question is any hard defence sustainable? And we certainly have a lot of them on the planet, and I suspect we're going to see more with the trends we're seeing. I think the challenge with defences is they buy time, I think is my way. Nothing is forever, and I think that if you're following through a certain strategy, it buys you time, and you have to invest and keep on choosing as a site to invest and keep it there. So I think there are these sort of timescales where maybe you can actually change your mind. There is the issue of locking, though. The Netherlands, for example, large areas below sea level, has very little choice. Either they keep protecting all the river dikes, I mean the dikes from the river, but they're linked to the coast, or they abandon their country. So there are some very difficult issues there. So I think I think you've asked a difficult question, and it's a very good question. And I don't think people understand the answers of how we can protect our coastal cities. I mean, I think it's particularly relevant to coastal cities. So that map I showed, all of those will have coastal defences. And what does that mean through the 21st century as sea levels get higher?
Rob, one of the things you didn't mention was mangroves that seem to be the natural defence of choice for much of the world, particularly in the tropics, but of course have great carbon capture benefits as well as biodiversity effects as well.
Yeah, I mean both in tropical regions, mangroves, but coral reefs as well. So coral reefs around the island absorb the wave energy that then doesn't break on. So if we can keep our mangroves healthy and keep our corals healthy, then they in themselves are sort of natural flood protection.
But just responding to Damon's point, I think one of the key messages to my mind is actually sustaining the habitats we've got, because you do go and see people planting mangroves in places where they just won't grow. So there's a lot of well-intentioned attempts at creation in the wrong places. So sustaining the Sundarbans, for example, sustaining the large mangrove systems we have, and the Sundarbans provides huge protection to the people of Bangladesh that live above them. It is the first, I think, thing I would recommend. And then you can obviously think about, we have in the UK managed realignment where we're recreating salt marshes and intertidal habitats on areas that were formerly intertidal. And again, so they're fit for purpose, and there are analogues for that in the tropics as well. But much of Bangladesh is talking about a green barrier along the whole coast, maybe 5 kilometres wide or something like that, of mangroves, which would seem feasible. To quantify the benefits is the challenge. What do they get for that? And I can't answer that.
Well, they get a lot of carbon credits, which would be one step. So there was a woman in the middle here.
Hi, just firstly, thank you for such an interesting talk. Obviously, this paper's a long time coming, report, and it is hopefully going to have a lot of influence on the house moving countries, government policy, social change, and all of that sort of thing. But as we're all aware, is missing now a key contender in terms of how large and how much of an influence America has. Does the report mitigate for the fact that some countries aren't necessarily currently planning on making any sort of changes, or is it solely everyone has to change now, and that is the only solution?
So first of all, it's important to remember that the IPCC process takes account of not just what the scientists say, but it's reviewed by governments around the world, and that also includes the US. And if they disagree with the content, this is the time to say it now. And all of the governments have agreed on the content of this report. And having gone through the report and looked at some of the comments, particularly the government comments, some of them are quite coarse, they're quite targeted. And you can see there's been a lot of debate, and a lot of that debate has happened this week. One of the things that we learned when Trump pulled out the Paris Agreement, well, first of all, it hasn't happened yet. He pulled out, but there is that timeline between actually not doing anything. It's still committed at the moment, and by that time, timescales, presidential timescales change, and who knows what will happen. But there are a lot of individuals, a lot of organisations that actually say, you know what, he might not do it, but we're still concerned anyway. So it's still actually coming through, even if it doesn't come from particular heads of government because they don't like that policy. So yes, I mean, when people don't sign up, it is challenging, and when people withdraw, it is challenging. But there are still other ways to do it, and there's still possibilities that you've got to keep in mind. Thank you.
If I just chip in, I wasn't involved in this report, but my experience from previous reports was the US provided more comments than any other country. So you get this big stack of review comments, and maybe 50% would be from US government, US scientists. So they're really engaging certainly historically they were engaging the process in a very powerful way, and a very constructive way, actually, these comments, yeah. I didn't necessarily like all of them, but they were good points.
Yeah, I found this stood out.
Gentleman here.
Yeah, thank you. In Robert's presentation, you you mentioned Volta, Ghana. Yes, it happens to be the place I've lived all my life, aside Southampton. And places such as Volta, Ghana are really feeling the impact of climate change already. It's devastating. There is the physical barrier that you showed. It's the intervention that's in place there, but it's not adequate, not enough. The land keeps being eroded frequently. I want to ask, is there any kind of correlation between the amount of contribution to this problem and the investment in the adaptations and the interventions that are being implemented? Those people who are causing more harm to the environment, are they investing enough to help people mitigate the impact or put in adaptations?
Well, I mean, I think that there are various adaptation funding mechanisms that have been agreed, and that the principle of those adaptation funding mechanisms is a sort of polluter pays principle, where a number of developed countries have agreed to provide funds for adaptation. Although my understanding is the amounts that people have signed up to them, but the amounts that were promised have not necessarily been forthcoming. But there is a sort of process in place which is trying to target adaptation funds, and then various agencies have become accredited that they are allowed to disperse these funds, and therefore projects can therefore be created by them, and so you will see investments. I think the major action is to come at this time, but somewhere like Bangladesh, where I've also worked, there is quite a lot of adaptation funding available within Bangladesh, although I would say, I mean, in many ways, I think actually one of the problems is getting projects that can be funded by these mechanisms. In Bangladesh there is money, it's actually linking it to actions that can be accredited by these processes. Because a key point about adaptation funds is they only pay the incremental costs of climate change. In other words, you have to separate what is not climate change from what is. And pretty much everywhere I go over the world's coasts, the problems are a mixture of global, regional and local drivers. And so you have to sort of start to think through what is what. And that maybe is an interesting, for young people in the room thinking about doing research questions, that's actually quite an interesting research frontier. Because to date, we haven't done much good quality attribution. And if you look at the IPCC 4th assessment and the IPCC 5th assessment, in coastal areas, the consensus is we can't redo it at the present time. So surprisingly enough, we're confident of the impacts in our models, but when you actually look at observations, it gets more difficult.
Thank you for the presentation. Another question for Rob. And the World's Great River Deltas, you talked just made a sort of passing comment saying, of course, we've got to think about substance as well. So I was wondering for the sites that you highlighted in the World's Great River Deltas, what's the relative magnitude of the substance effect on top of sea level change? And does that mean as well that we've got to look to the upstream in terms of water supply coming down, and also water extraction, which must be a big driver of substance, especially in Southeast Asia, for instance?
Well, deltas are subject to many stresses. I mean, in fact, the answer to the previous question, I suppose, it's this climate change effect, but there's also all these catchment management effects, which are sort of a regional effect that's causing big changes. In the Volta, there aren't really good substance measurements, but we think it's small. The Mahanadi is similar, and we think it's small, and the Ganges Brahmaputra, sort of in a meta-analysis, 2 to 3 millimeters. There are hotspots. So probably there are other deltas where there's a lot more going on. The Mekong, for example, is somewhere where there's very large rates of substance going on. But I think in terms of trying to think of more working with nature and maybe more, if you like, long-term ways of working with these problems, certainly taking the sediments that are available and trying to use them. In a sense, we tend to treat sediments as a pollutant, don't we, really? And almost want to get rid of the stuff. but actually allowing it onto the land, the nutrients that are on the land. Obviously, I think you guys sitting there know a lot more about this than I do. But I think that's something that needs to be taken on board, and that clearly involves thinking about the catchments. But there's a lot of competing interests there, and back to that, my talk about barriers, conflict, because the people who are upstream may not benefit much from the deltas doing well. So there are difficulties there. But
did you say 2 to 3 millimetres for the Ganges groundwater?
On average, Sally, would you like to comment?
So,
She's the lead author of the paper.
yeah. So I looked at this a few years ago and found about 200 measurements of substance in the Ganges from future. And the data was quite messy. There were some measurements going up to about 12 millimetres per year. Not sure I believe all of them. Others were about 1 millimetre per year. But about 3 millimetres was about right across the delta. But Robert said there are hot spots.
That's right. That's natural. That's the groundwater abstraction reduced.
Sorry, the 3.
Is that natural background substance? That's compaction. I was really concerned about what groundwater abstraction does to substance rather than the natural.
There doesn't seem to be much groundwater extraction. I mean, I think partly because of things like arsenic in the groundwater, there isn't the large extraction of groundwater you see in some other deltas. And also, they do use the water. There is actually seasonal mining of groundwater, but the monsoon is so intense that it tends to recharge. So right now it's not maybe unsustainable. So it doesn't seem to be as big as you see in many other deltas. But I agree, there's a diversity of results there.
But you both have done a lot of interesting work looking at subsidence in cities with groundwater. You see that up to 2 metres of subsidence in some of the major cities.
Or 4.5 meters in Tokyo.
Yeah.
So no, I mean, I actually had a slide on substance in the talk, and I took it out because I thought it might actually distract from the message about 1.5. But as I was raising, I mean, cities in deltas where you do pump groundwater, we have seen many meters of subsidence, much larger. In fact, the rates we talked to 2,300, we've seen in Tokyo, it's happened. Between 1920 and 1960, they pumped a lot of groundwater out. Then they recognised this was a problem, and they've actually brought in surface water, and they've stopped and actually do massive recharge, and they've actually stabilised it, and it's not subsiding anymore. But 1 million people in Tokyo live behind large dikes below sea level, depending on pumping of surface water, etc. It is a little Holland, if you like. Obviously, Tokyo is a big city, but around the port area, there is a large area that is just like the Netherlands.
Gentleman here. And then
you were talking about the coral reefs and how they're being affected by the increase in temperature. And I was also wondering, with the increase in sea level rise, does that go to that, obviously that will be until 2300 or 2300. Will coral reefs be able to survive in the future, or will the increase in ocean acidification as well as fluxes in the ocean will that affect them negatively as well?
The first point coming out of it is that the coral reefs are probably more likely to disintegrate and die first because of the rapid changes in ocean temperature, also ocean acidification as well. There was a paper out recently looking at depth of water that corals can survive, and I can't remember the outcome. Are you going to be able to put that?
Yeah, there's a paper in Nature out earlier this year, and it's quite regionally diverse. This is not talking about ocean temperature scores, it's just purely summarised. There's some regions where they think the corals can keep up, there's other regions where they think it can't. It's quite a complicated picture. The really interesting thing I think with corals is we often think about sort of small island states being slowly swamped by sort of sea level rise, but I think there might be these sort of triggering points where suddenly, with a particular threshold of sea level rise, the corals won't be able to keep up, and then you'll get all of the wave energy sort of focused directly on the coast. But the person you want to speak to is Jörg Wiedemann. Here does a lot of work on corals, and certainly with ocean warming, he thinks easily in the next sort of 70 years there might be no corals whatsoever. I think they're doing some interesting work at the moment looking at what's they called them, Damien, coral arcs.
yeah,
They're
future.
actually trying to create things you can put in the water that would actually encourage coral growth and sort of save corals. And but Jörg Wiedemann, look him up and go and have a chat with him.
I mean, I think the main thing with corals, the bigger danger before sea level change or temperature or pH is actually just pollution. Pollution and turbidity will kill them faster, and nitrates will kill them faster than any of these effects. So actually, if you don't deal with that, you know, on a short term, that's going to take over before these slightly longer term.
I suppose I should say that I showed you the Maldives capital. All the reefs around the capital is there. So I mean, you know, so it is very hard to have high concentrations of people in live corals. So I mean,
yeah, and then there's blast fishing and all sorts of things as well. Is it woman at the back?
Hi, thank you for the presentation. My question is about do you know what will be the impact on the water and especially on the wave climate of the sea level rise? Do you have an idea?
There's a lot of uncertainty, and that's partly why we can mention it. So a lot of work has been done sort of looking at changes in storminess, and it's quite mixed. So if you take, for example, the North Sea, several studies suggest that there will be more storms, which will increase the storm surge climate, will increase the wave height, but most of the studies show that that's within the level of natural variability. So generally speaking, the previous IPCC reports have sort of had low confidence. It's a slightly different picture when it comes to hurricanes, and again, it's quite regionally diverse. So if you take Australia, for example, there's little consensus on this, but there's a feeling there'll be less hurricanes, but there'll be more. Potentially, they'll move further south. Now, I mean, the interesting thing with, obviously, if we can achieve 1.5, is that some of those negative effects to do with changes in storms and waves will hopefully come down. But certainly some of the work we've done with FIRS, I think mean sea level rise is always going to be the dominant factor. Robert and I did some simple exercises, and we have to have an enormous change in the frequency of events to kind of offset just that simple 1 meter rise in sea level. Anything to add?
Well, I think again, it's thinking about what's the question with waves, because there's the question about what's happening in the ocean and the waves that are actually coming into the coast. But once the wave gets into intermediate and shallow water depths and is transforming, if you have deeper water, the waves will lose less energy, so there's more wave energy at the coast. It's simple physics, and so that's an effect. That's an effect of sea level rise. I always see that, and beaches erode in response. That's things like the Broom Rule, various ideas around equilibrium profiles. So I think it's good to be precise, but certainly, I mean, rising sea level have a huge effect on the waves hitting the coast, and the coast morphologically will normally respond.
I mean, there have been a number of studies that show that actually changes in wave direction can have very significant effects on sort of erosion.
Gentleman here, then up the back, and then over there. Yeah.
Thanks. I have a question about the orders of magnitude for different predictions and impacts. The one slide that you showed, Dr. Sally, from going 1.5 to 2, then 2.5, then 3.5, it seemed so proportional to me. I mean, if I plot something at 6, it would be, again, I think easily do it. It seems so proportional. Is it really proportional? And the second thing about impacts, that how much can we take, or what is the gain going from 2.5 to 2, or from the 2 to 1.5 that this report suggests?
So when you mean about proportional, was that the slide about sea level? The first one.
Like where you had the 2,300 and you had like projections.
Yeah, so the sea level projections, those projections were generated assuming that all the processes that have happened historically continue to happen in the future and continue to respond in the same way to warming as they have in the past. What those projections did not have in is thresholds and tipping points in the system whereby you could suddenly destabilise a large ice sheet because the limit has gone above a certain level. Those things would be on top of the projections we showed. So that's why it looked very smooth. In terms of those, the likelihood of them occurring increases as the warming increases. So if you go, say, some people think there are these thresholds between 1.5 and 2, but certainly if you go beyond 2, the likelihood of crossing some threshold whereby some ice sheets will be stabilised increases.
So onto the impact side, this really comes down to what does like a 1.5 degree or a 2 degree or a 2.5 degree work. Because if you take the period of time of when 1.5 degrees occurs compared to a 2 degree, you probably won't get that much change. But actually, when you consider it, the longevity of that change is actually really important, because if you just see here, it just flattens off. And it's that longevity that actually then makes that difference rather than the actual temperature when it first occurs. And that's something really, even when I was writing the report, we had to fill out a big grid, and I was putting these numbers and they look tiny, and I was like, I know they're not tiny. And trying to communicate that to people is really, really hard to say. It's not just what happens immediately, it's that long-term impacts that actually can actually make a difference on the coast and see what that really means to sea level rise.
If I just chip in as well, I think there is another special report on the oceans and cryosphere, which is working at the moment. We'll be publishing fairly soon, we might be reviewing that. And so they're actually addressing this question of thresholds very explicitly. So there should be some interesting insights, probably quite soon, from that process. But again, it's not reporting for a year or so.
Couple more questions. Gentleman right at the back.
So your presentation mentioned a lot on the coastal flooding side of things, but what about coastal erosion? Was that not covered by the IPCC report? I suppose the relative increase of coastal erosion, what's that likely to be as a result of warming?
So the report itself specifically has to look at 1.5 and 2 degrees. So that was something that, including the Government of America, really pinpointed that we had to do, because there just wasn't room in the report to say that. So all the comments were, we really have to focus on the 1.5 versus 2 degree question. It meant that in the time period we had, we only had a certain amount of literature available to review, because it just hasn't been written, it hasn't been researched yet. So therefore the emphasis wasn't flooding. I looked around for papers on erosion, and it was actually, there weren't any papers that were specifically looking at 1.5 and 2. There were a few papers which did say we can actually detect shoreline changes in some areas of the world, but we think it's due to sea level rise because we can't explain them any other way. So those shoreline changes, I can't remember whether accretion or erosion offhand, but again, if they were erosion, I'm guessing they were, it does actually shoreline retreat, I should say, it does actually suggest that actually sea level rise is making a difference. The other aspect that was coming up was, I think it was a paper from Japan, where it was looking at coastal squeeze. So the notion that if you've got a fixed sea wall, say, and with sea level rise, your beach is getting thinner and thinner and thinner. And again, they were looking at projections using the RCP 845, this non-mitigation scenario, and one of their conclusions that we would see beach thinning with sea level rise. So again, it's not a 1.5 versus 2 question, but there certainly is a lot of potential for more erosion, particularly with fixed structures involved. But we also have to remember that if we get more erosion, it often can mean more sediment to beach that we were looking like a cliff. And so that can actually slow erosion down as well. So there is that sort of interplay between the two that goes in cycles about larger events. So yes, I think you would potentially experience more increased erosion, but there's a lot more factors to think about as well.
And I think this attribute, I mentioned the attribution question again. It's not maybe answering your question specifically, but I think there's an interesting question about how much of the erosion that we're seeing on the world's coast is due to climate-induced sea level rise, and how much is due to other factors, for example, beach mining, or the fact that sediment is no longer reaching the coast. And we don't really, conceptually we understand this, quantitatively we not. So these are big research questions, which, again, back to those people out there interested in research, these are kinds of things people can do PhDs on.
Couple more questions before we have
Hello. Sorry. First of all, thank you for the presentation. I hope I won't go too much off topic, but I've always been baffled about the different contribution to climate change by well-developed countries and third world countries. And what I found confusing is in many cases, we have third world countries that have to pay the worst consequences or some serious consequences. So my question is, I was just wondering if if this topic has ever been brought to discussion during the Paris Agreement. I tried to make it more simple. I'm a bit confused as well. Like, what I'm trying to say is, if I pollute more in my country, in my own regulation, I'm expected to pay more, right? So my point is, if we live in a globalized world, we are starting to have globalized global regulation. Why wouldn't the countries that polluted more contribute more? If that has been brought up as a discussion, that's my point.
So there was, in terms of thinking about specifically to start with, there was one paper I read, I think it's the author was Harrington, and what he said was that when you look at climate change, you look at global warming, it happens to be the countries that are situated, they happen to be developing countries basically around the world. It's just by chance, rather than being saying global attitudes. That's just happened. And so that not only are those developing countries going to be worse off because they was the cause of the problem, but and they have other struggles going on, they are actually going to be hit first. And that, I think, is the first important point. And that was only, it wasn't covered in the chapter that I worked on, so I don't know what discussions went on there. I think this idea of equity and the proportionality is still, again, being debated. I think the work that I read in the literature, it's being pointed out that, hold on, there is an equitable effect. And I have recently had a paper accepted where we looked at that, and again, we were finding impacts were actually disproportionate to, say, emissions, or impacts were disproportionate to GDP for some countries. Indonesia was one of those that particularly stood out in different ways when I was looking at the effects of the weapons that could potentially be lost. But I think that's a discussion that's going to come out much more in the next few years. And what would be really interesting is that when all these governments next meet in Poland next, that's kind of the debate that will be going on, looking around, well, what does this report actually mean for governments, not just in terms of mitigation, but actually looking at how do you offset impacts. There's still a lot of debate there, you're absolutely right.
So, you know, the percentage of emissions that are...
So yeah, because the warming is related to the total amount of carbon emitted, there has been efforts to just sum up the amount of carbon which probably is emitted up to now, and then say, well, they're responsible for that fraction of the global damages. It's one thing to do it scientifically, it's another thing to get countries to agree that some kind of equitable solution is something which. So I think it's actually relatively easy to come up with a scientific rule of thumb based on this total amount of carbon emitted, but it's very hard to then turn that into something.
And one of the things, again, working with the Maldivian government, we found is that because they're lots of islands, about 1,000 islands, very dispersed country, they've obviously got boats, they go around, but they also have to use the air a lot as well. And so even for that, a country there, they potentially then have a lot higher emissions just because of the nature and the geography of their country. So you could come back and say, okay, from one science, from your maybe from the physical science point of view, you could take that, but the human scientists, human geographers, might actually come back and say, actually, there's more economics, there's more things you need to think about that. So even within the science community, you get a lot of debate.
I think, that was the remarkable thing about Paris, wasn't it, really, that there was this, one of the blocking stones for many of these agreements in previous meetings had been this tension between the historic polluters and those who wish to develop more, who were going to suffer the consequences. And I think that the big step forward in Paris was that actually people generally agreed that they both had to work together, though this equity is a long way from being achieved. And you know, these less resilient parts of the world will be the parts that suffer most. One quick question, and then from the gentleman at the back again, if it's going to be quick. Oh, sorry, I can't see you there. There's a man down here as well. Okay.
Also, thank you for your presentation and talk. And talking about third world countries right now and the economies, they will go through a very rapid development in the years to come. And let's think about the energy industry as like a simple example. So the way they're going to develop, are they aware of the implications of the development that, like, say, the westernized countries have gone through? So are they planning to build carbon-emitting power plants, or are they already aware of the impacts that their industrial development could have for the future?
I can answer that.
I wouldn't consider myself an expert in this area, but I think you've hit another problem, really, isn't it? I mean, there's been various IPCC, there's been a special report on technology transfer some time ago now, but it was all about how do we roll out the best technologies quickly so that development can be sort of lower carbon or carbon neutral. And I think that's one, I mean, certainly in Southampton we have a lot of expertise, some of it's in the room, and that's one of the big thrusts about replacing carbon emitting with low carbon emitting or non-carbon emitting technologies. And that's something that really has to be pushed forward. I imagine that the discussions at the COP meetings, where this is where the countries meet, will be partly about how do we actually get these technologies moved around, and also financial incentives, because I mean, there's often maybe cost humps to go over to try and get them. I can't answer the question very well, but I think you're thinking along the right lines.
If you looked at the energy mix, and we hear a lot about renewables and investments in renewables, particularly in China, that's really forged ahead with solar cell and winds. But if you look at the global energy mix, for example, the amount of coal being burnt at the moment is about the same percentage level as it was in 1997. So although it's decreased in the noughties, it's gone back up again. Because there's been huge investment in coal-fired power plants, because that's the most readily available source of high-density fuel.
Yeah. And I could imagine that it's a very difficult political discussion, because the third world countries would be saying that all you westernized countries, you've been destroying the environment, you've had the coal power plant, so why shouldn't we allow to have these coal power plants as they are sufficient?
So I've just looked at my crib sheet. So the IPCC sent out a useful crib sheet of difficult questions of which you just asked Colin on. So each of the countries have set out intentions for reducing their own emissions. So these were INDC's intended nationally determined contributions. And this was done, I think it was just before Paris, so I was looking at the scenarios then, I'm trying to think of my timescales. And that's what they intend to do. And that's what, when we look at future scenarios, all of those intentions are being added up to look at emissions that then translate into temperature. So they are thinking ahead, much as our government would now, about how are they going to reduce, or can they reduce emissions? Because it's very difficult to have that balance, because yes, all countries want to develop, and you can't just change energy overnight. But there is that joint government thinking, even if you don't see it straight away, that there has to be a shift, and enabling that shift to happen is really, really difficult. The other thing that I've actually done before, if you Google Maldives and oil, you actually find that the government's looking at oil because they think they discovered oil around their waters. So, even that, there's controversies there about actually you might discover it, but what do you do about it? So there's a lot of things to think about, and a lot of challenges ahead on that.
I mean, I think that the UN has to come clean here, that the intentions did not add up to 2 degrees, let alone 1.5 degrees. And the actual implementations are nowhere close to it.
Yeah, so
on here, this bit of the graph here shows what the nationally determined contributions add up to 2030. And they still see the emissions rising year on year out to 2030. that, to get to 1.5, you actually have to stop emitting carbon in about 15 years after 2030. So they're nowhere near 1.5 degrees.
You guys were telling me some interesting facts earlier about the percentage of renewable energy needed.
Yeah, so what I heard today in the back of my, correct me if I'm wrong on this, is that we currently globally have about 25% of the energy resources of the renewable energy, but we need to try and target 85 to get down to that 1.5 level. Again, our useful sheet of information also says that depending on choices after 2030, we're on track to 3 to 4 degrees worth of warming, and we really need to accelerate in reducing emissions to try and achieve 1.5 because we're nowhere near that limit, and that's what the governments need to review and review their commitments.
And I suppose what I was going to say, things like aviation was mentioned by Phil. I mean, I'm sure probably look around the room, probably most of us fly, and you know, and aviation is growing phenomenally. So there are also these sectors which, again, at Brexit, Britain's talking we're open for business. Suddenly it's going to be lots more flights to further. So there are tensions in government policies. You know, most governments want more transportation. So how do you reconcile these things? And it's difficult.
Just in terms of closing, can I put you on the spot, Sam? You are a superstar here. You're the only person in the room who was an author on this report. So what can everyone here do to help us achieve 1.5? I think there's always a sort of top-down in terms of government. I think there's a sort of bottom-up approach. Have you got any?
Big question.
Should we be writing to our MPs? What can we do? I mean, we can obviously fly less. Is there anything else we can do?
The most effective.
Choices at the end of the day about what, how you would like to live and about the consequences of your actions. Because one of the things that the report shows, it is going to happen within your lifetime. And I think the thing that struck me this morning and over the weekend when I was rereading the report is about the thing about corals. And you think, this is like, sorry, I'm like corals by the way, the little Finding Nemo fish is like, is that little fish died? Oh, Nemo died? You don't have any corals? And it's those kind of questions that you just don't think will happen. I think what's come out today is that those things do or will happen, and we will see them and look forward to doing something about it.
Well, I'd say we need a technological revolution because to really to achieve this, it's not the world we live in today. And also, I think that the timescale of climate change, there'll be a lot of interest in the issue for a few days, but then it will die down. And the political cycle is operating at a much shorter timescale. So it's important to maintain pressure. And I'm not sure whether we get to 1.5 or 2 degrees, but the nudge so that we move to lower carbon and we make it feasible and possible. So and I'm always amazed that sometimes you can cross over humps and things can happen very quickly. So I think it's important. So I think that's the most important thing, to not let the issue kind of go on the back burner, just make sure that governments are very interested in it. And so I think campaigning about it really it is important.
Yeah. I mean, I was absolutely fascinated about that Thailand cave rescue. And there was a beautiful quote that came out of that. It said that if all the world's countries can come together, they can achieve some incredible things, rescuing those 13 boys. Yeah, so I think, if we do come together, we can achieve this, but it's going to take time.
That's also a question on my difficult sheet as well.
Sorry, I'll be honest.
There's a very nice website called Carbon Scorecard, I think it is, that you can look to see at every country's intention with Paris, what's actually been enacted, how far it will take you, where the intentions take you, where business as usual take you. That it's quite fascinating to look at, albeit somewhat depressing. It's good to see so many early career researchers and students here today, because really these are going to be problems that influence, really affect your lives and the lives of your children and grandchildren. So maybe you'd like to help me to thank our speakers and panellists today. my understanding that the most carbon effective thing you can do as a person, as an individual, or maybe as two individuals, is to have one less child. That all of us are these carbon-eating machines that travel and need to be kept warm, and actually just more people, particularly in the developed world, really have huge impacts on the climate budgets. So thank you to the panellists, and thank you for coming along tonight.
Can I just also thank Hashim and Abby? I was expecting there just to be 5 blue chairs here. I was very impressed when I saw all of these printed out. So can we just thank Abby and Hashim? Thank you. Have a good evening.
So this will be available somewhere, won't it, this presentation?
Yes.
Yeah. But just remember that downloading things off the web is a major source of CO2 these days.
It was recorded, yeah. The problem is the voice in this room is pretty bad. So I really hope it was my students, because I recorded last night.